Now some parametric variations in a capacitor, which is what I'm going to take to, right? So let me imagine a capacitance of this kind. With area of overlap A and separation between the two plates as D. Right? Now I fill this space partially with a dielectric. This space between the two plates of the capacitor I fill partially with a dielectric. This is a dielectric of dielectric constant K and of thickness T. So there is T units of a dielectric of dielectric constant K and D minus T units of air. D minus T units of air. Yes or no? The rest is air, D minus T units. And let's say this plate has surface charge density sigma. This is minus sigma. Sigma, of course, is Q by A. Now, minus sigma. In the air region, the electric field is going to be sigma by epsilon naught. In the air region, the electric field is going to be sigma by epsilon naught, right? When these electric lines of force enter the dielectric, this is the dielectric. When these electric lines of force enter the dielectric, they will get weakened. They will get weakened by a factor K. That means now the electric field in the dielectric becomes sigma by K epsilon naught. Once they emerge from the dielectric, they are restored back to sigma by epsilon naught. Yes or no? Right? Now, so there is T units of the dielectric and D minus T units of air. The total potential drop difference between the plates of the capacitor from the positive to the negative plate, the drop in potential will become the drop because of the air region plus the drop because of the dielectric. The drop because of the air region is going to be sigma by epsilon naught, that's the electric field in the air region, into the total traversal in the air region, which is D minus T. That's a drop in the air region plus the drop in the dielectric, T units of the dielectric, which is sigma by K epsilon naught into T. Yes or no? Right? Now, by definition then, say if Q is the charge here, which is sigma by epsilon naught minus Q is the charge here, then Q by V would be the capacitance of this arrangement. Q by V would be the capacitance of this arrangement. Yes or no? The charge on the two plates, Q divided by the potential difference between the two plates. That's the definition of the capacitance of this arrangement, right? Now this sigma I can write as Q by A, right? And I can bring this Q here, right? Clear? Now Q by V will be the capacitance of this arrangement. Q by V will be the capacitance of this arrangement. This arrangement then becomes 1 by Q by V, that is 1 by C. C is the capacitance of this arrangement, and that is like 1 by epsilon naught A by D minus T plus 1 by K times epsilon naught A divided by T. Now epsilon naught A by D minus T is like an air capacitor. Epsilon naught A by D minus T is like an air capacitor with area of overlap A and separation between the two plates D minus T, right? That's an air capacitor. And K times epsilon naught A by T is like a dielectric capacitor filled with dielectric. And of thickness T. This is the dielectric. Right? Which means this arrangement is like two capacitors in series. 1 by C is like 1 by C of air plus 1 by C of the dielectric. That means this arrangement could be replaced by two capacitors in series. Because see, 1 by C is 1 by C1 plus 1 by C2. So it's like C1 and C2 must be in series, right? So this arrangement is like two capacitors, an air capacitor, separation D minus T, and T units of a dielectric capacitor. Yes or no? Right? Where epsilon naught A by D minus T is the capacitance of the air unit. Bless you. And K times epsilon naught A by T is like the capacitance of the dielectric unit. Right? So 1 by C is like 1 by C of air plus 1 by C of the dielectric. 1 by C of this arrangement is like 1 by C air plus 1 by C dielectric. It's as if you coagulate the air units, D minus T units and T units of the dielectric and connect them in series. This arrangement is like these two capacitors connected in series across the arrangement. Clear? And it does not depend on the exact location of the dielectric in this region. Do you realize that? This dielectric could float anywhere in this region and it will give you the same arrangement of the capacitor. Yes or no? Now, if this was a conductor, then K will become infinity. K will become infinity. In fact, the electric field here will become 0. If K becomes infinity, this part will become 0. 1 by C of the dielectric will become 0. Right? Then the whole thing is like just D minus T units of a air capacitor. The whole thing then gets reduced to a D minus T units of a air capacitor. If K is infinity, this is like a conductor then. And in a conductor, so there would be electric field which would be 0. So there would be no potential drop in T units. The entire potential drops only in the air portion. And it's just like an air capacitor of separation between the plates, D minus 2 units. This will become ineffective if this was a conductor. Clear? Now, suppose there is an arrangement of this kind. This is a capacitor, separation between the two plates D, and this region is filled with a dielectric K1 and another dielectric K2. Between the two plates, and I want to be able to find the capacitance between P and Q of this arrangement. Now, when I want to find the capacitance between P and Q, it's as if I'm going to connect a battery between P and Q. Now if I connect a battery between P and Q, then the drop across this unit is the same as drop across this unit. The whole thing then behaves like a capacitor K1 and a capacitor K2 in parallel. This will behave like capacitor K1 and capacitor K2 in parallel between points P and Q, because the drop across this capacitor unit is the same as the potential drop across this capacitor unit. This arrangement actually behaves like a capacitor K1 and a capacitor K2 in parallel between P and Q. Suppose A1 is the area of overlap here and A2 is the area of overlap here, then C1, the capacitance of this unit, is going to be K1 times epsilon naught A1 divided by D. The capacitance of this is going to be C2, which is K2 into epsilon naught A2, the area of overlap of this divided by D. It will be like this would be C1 and this would be C2. C1 and C2 would be in parallel. The equivalent capacitance between P and Q of this arrangement is going to be simply C1 plus C2. If you had something like, can I wipe this off? Make sense? Say this was K1, this was K2, and this was K3. An arrangement of this kind, for example, between points P and Q. And I want to find the capacitance of this unit between P and Q. So this would have capacitance C1, this portion would have capacitance C2, this portion would have capacitance C3. It's as if K2 and K3 are in series with each other and in parallel with K1. So this reduces to K1 and K2 in series, that is C1 in series with C2, and the whole thing in parallel with, C2 and C3 in series, C2 and C3 in series, and the whole arrangement in parallel with C1 between points P and Q. So C2 and C3 in series would be like C2 C3 by C2 plus C3 plus C1 would be the capacitance of this arrangement, isn't it? C2 C3 by C2 plus C3 plus C1 would be the capacitance across P, where what would be C1? C1 would be K1 epsilon naught A1 by D. K2 would be, C2 would be K2 epsilon naught, say A2 divided by T1. C3 would be K3 epsilon naught A2 divided by, say, T2, kind of a thing. Yes or no? Clear? Now, you could have had a dielectric medium between the plates of the capacitor, which could be continuously varying, Suppose this is x equal to 0, this is the x direction, and this plate is x equal to d. And this is the dielectric in which K is not a constant. The dielectric constant is not a constant. It's a function of x. It's varying in the x direction continuously. Somebody could tell you kx is like ax plus b, for example. It could be linearly varying with x, right? Then what you could do is, you could break this into smaller portions. Say, this behaves, this is a small capacitor by itself, this is a small capacitor by itself. I choose this at x, at some x, the k of this over this very small separation dx. Dx is the separation between these two plates, right? The k here remains practically the same. So this behaves like a capacitance dc, which is k at x into epsilon naught a. A is the area of overlap of these two plates, divided by, let's say, the separation between the two plates, dx. So 1 by dc, 1 by the capacitance of this portion is going to be dx divided by k at x into epsilon naught a. That's the reciprocal of the capacitance of this small chosen strip, right? Now you have several of these DCs in series. Between P and Q, you have several of these DCs in series. So what would you do? 1 by DC of this plus 1 by DC of this plus 1 by DC of this, starting from x equal to 0 to x equal to d. You would add all the 1 by DCs, and 1 by DCs will give you reciprocal of the equivalent capacitance, isn't it? In series, that's what you do. You add the reciprocals of each constituent capacitance, and you get reciprocal of the equivalent capacitance. So then you would have to add 1 by DCs. You would have to add 1 by DCs. If you add 1 by DCs, then the 1 by C equivalent, adding 1 by DC, is adding dx by k at x into epsilon naught a, where x runs from 0 to d. Now if k is known as a function of x, or is given to you, you can plug in the same, integrate this between the limit 0 and d, you would get 1 by C equivalent of this arrangement. Yes or no? Simple, right?